Thank you. Can you hear well? So today I'll just briefly introduce what Groupon, maybe people here have used Groupon before in the United States. It's a very popular app and within the top 6 of all time. We are actually bringing a lot of money into the local commerce because we do local e-commerce. And we receive many users during the day and seeking for the best deals possible. We also diversified, so Groupon has become or is becoming the daily habit for purchases online on multiple categories. So we have the local e-commerce category, but now we're competing in regular goods, or what we call just regular e-commerce, as well as travel. So in fact, Groupon business has been growing in all these 3 verticals, and which makes it a very interesting problem because it not only looks at what people can buy in the vicinity, but it also looks at what can they do in the future, et cetera. So today I'd like to walk you through 4 different use cases and explain a little bit of how we use machine learning and deep learning within Groupon to solve some of these use cases. Going from the more generic use case, which is when the user opens the app and they get just plain recommendations based on who they are, where they are, and what they've purchased in the past. And then I will walk you through the use case of browse, when someone actually is exploring the different categories available in Groupon. And then the third use case is search. So when the user intent is more clear, they type in something and they're actually expecting results. And the final is more like similar deals. So if someone already purchased something, what else can you upsell or cross-sell? So let's start with just statistical machine learning models, and then we'll get more into the deep learning part. So the home feed is where users go, and they could be signed-in users, but normally users that have the app downloaded and have done some purchases in the past have some profile history. So the idea is, or the challenge here is, given the user the context, which includes the location of the user, time of day, whether they're on the mobile web app or on the website, as well as the deal features. And by deals, every deal has its own characteristics. The price, of course, the discount that the deal has, the description, the title, all these different features. How can we present to the user the optimal list? And that's the recommended problem. How do we formulate a list of recommendations that is optimal for this user? And as we'll see also, it's also important that Groupon and the merchants make money. So it's not just about the user's intent or what the user's more convenient thing is also behind it an objective. And then we have to do this under a very strict constraint, because if we want to use machine learning, especially point-wise scoring, then we have to score each one of these deals in microseconds in order to bring him or her a list of results in order time. And then most importantly, I mean, or a different factor is that you have to create this quickly, considering a huge mass of data that is provided with all the transactions that the users have done, with all the similar transactions that other users have done, and of course with the moving target of the database of deals. So our initial stab at this problem, we looked at obviously 2 different phases. The offline training phase, how we can take and amass all this data and create models. And it just naturally fit within the H2O sparkling water use case. We've looked at we started with GBM and linear models, ensembles, but most importantly, we looked at event data that we're gathering on what users transact on. Very important is also their redemption location, because not only users buy a Groupon or a coupon, but when they go and redeem it, they do it at a later stage. Now on the online scoring side, I think something unique that we've implemented is that we've embedded the machine learning model into a search engine. So we actually built something called a learning to rank plugin. What that is a piece of code that actually loads a Mojo and scores the deals within Elasticsearch. Now, this concept of learning to rank is not new. I think what is really interesting is that that does provide you with low latency scoring and co-location of data between the browsing search capability, so you can use the normal text search and the ability to filter results and sort results. And then you also have the model that can use for scoring. At a high level, the architecture contains a so-called feature store that contains most of the features that the deal, as well as the information about what users have purchased in the past, the event level data, and that includes what they purchased, when they purchased it, and when they redeemed it, right? And the whole idea here is to join this primarily time-based joins with respect to attributions. We want to know when was an impression or when was this deal shown to the user, and which one of those impressions or deals that were shown to the user actually led to a purchase or a conversion. There's also other signals, like when someone views a deal and opens up information about the deal, but they don't purchase it. That gives us another signal. And then ultimately, when they go and redeem the deal in the local merchant. During that, in that process, we have created an ML pipeline that suited our needs. Now, the ML pipeline we created has different components to it. Just going to mention a few in interest of time. But as we do the feature transformations and we store the feature transformations along with the mojos, we also do something that's called model decay evaluation. And I'll show an example of that. But primarily, once we create a model, we want to hinge cast or backtest along for the larger set of test data. Normally, when you create a supervised learning model, you have the training set and your test set. But now, since we keep a huge record of transactions in the past, we do hinge set, or basically backtesting of the model. We also keep accumulating, and before we're launching a new model, do forward testing with the new data that's coming in. And we keep doing that, trying to visualize if a model decays. So this is fundamentally a time series problem, because as you are learning, the machine is capturing all these events and doing all these scoring. Time changes, season changes, people change, and therefore you have to retrain the model every once in a while. So we have to be able to identify when is that the model decays in order for us to retrain. And then the problem of actual model evaluation we solve through offline evaluation, looking at the typical AUC and other metrics, as well as A/B testing. So everything that we do actually goes through a test that is exposed to the user as an experiment, and then that is captured, and we release multiple models at the same time. So pretty much using an ensemble approach to picking the best of the fittest models out there. An example of this model decay concept is shown here. So basically, once we are launching a model, we backtest it against historical data, but we also don't launch it immediately, capture several days in the future, and try to do forward testing not only with the data we trained on, but with the data that we're accumulating during those 2-3 days after the model is released. And then we continue monitoring, trying to figure out if the model decays. And once it does, we retrain. So it's kind of a trigger-based approach, a monitoring-based approach, instead of a cadence of a weekly training on the data. We also look at other non-traditional metrics. By non-traditional, you've heard of obviously AUC, or area under the curve, percentage of RSME or RMSE, and so on and so forth. But there are some ranking metrics that depends on where in the list users actually clicked on and purchased from what it was presented. So one of them is mean average precision. There's also NDCG or NDCCG that looks at not only what was shown in relative to the score, but also in which position, and has a discount. So obviously, if I click on something that's on the top, I did a good job. As I go down the list and people scroll more, then the model is not doing as great because it's kind of having the user go and do more work to find what they're looking for. One important aspect of Groupon is that because we serve multiple businesses, one of the problems is, okay, a model can be great, but it has to be kind of fair with the different actors or the different inventory that we have. So we look at mix, and mix between the different inventory, whether it's travel, goods, or local. And every time a model is launched, we look at changes that are too drastic that could occur because we have basically 3 different customers that we serve. And we don't want to absolutely make changes that will affect their overall individual business. But we do look at this as a portfolio optimization problem because ultimately, as a whole, we want to maximize return while trying to minimize the impact on changes or fluctuations in the business. Similar in price range, it turns out that price is something that we are very sensitive to. Obviously, the deals is what users are looking for. So when algorithms suddenly start recommending too pricey of a deal, even if the model says it's correct, we looked at those as red flags and actually validate them against the user's behavior. So what were the initial pain points when we launched machine learning models? One is that we understood that prediction was not the only factor in the game. Most importantly, how do you measure, how do you establish what a good ranking is, what's optimal? It turns out that while deals could be very interesting for user from a perspective of they're cheap and they're close by, they're convenient, Groupon may not be making enough money out of them. So it's similar, this is a two-sided marketplace, so the merchants have to be able to capitalize on leads and also on the amount of money that they make. So defining that objective function that is a balance between the user's intent and what the user would really like to buy and what the merchants and Groupon can benefit or profit from is a difficult task. And it's something that is not non-trivial, especially if you think about the different businesses, because the price range between a pizza deal or a local massage or a parlor and a travel to Taiwan is very different. So also the probability of someone purchasing one deal and the amount of data you gather for each one of these businesses is quite difficult and quite different. So that is one of the issues. The other issue was scaling this and doing this online within Elasticsearch had some limitations. So we were able to fit in trees that were shallow trees, 15 trees in more or less 3 or 4 levels of depth. But more than that, required us to beef up the Elasticsearch machines, which were already large. And we quickly realized that we could not do online scoring with very complex models. So what we did was that we created a two-step approach. So one, what can we score offline based on the quality of the deals and the information we know about the deals and historical information we know about the categories of the deals and how they perform in the past. So that we called deal quality score. We generate that offline. We also generate it based on permutations of gender and distance buckets. Distance is an important aspect of this. And then we compute that completely offline. And then online, we use the more contextual and user features that are only available in online scoring. And with that approach, we were able to combine a more complex model of hundreds of trees and information and features that we could not fit in the online scoring model with the online scoring. And then doing machine learning at scale is tough. I mean, that's not a easy say. So for that, we basically built a machine learning pipeline at scale with a standardized data science platform where transformations could be done, features could be loaded, and a reproducible set of actions that led to model generation and uploading. So now I'm going to mention a little bit about the deep learning applications. So one of them that I found very interesting is, what is the effect of images on people's decision to buy things? So we set out the task of trying to process images to understand their propensity or how they affect the propensity to purchase. So obviously here, I don't know about you, but obviously here, which hamburger you'd like to take a bite of, a picture is worth 1,000 words. The reality is we had the data. We had all the images in the catalogs that correspond to each one of the deals, and we also knew what people were purchasing, what people were clicking on. So we trained a neural net, convolutional neural network, to essentially predict not what the picture was. So we didn't do this to classify this as a hamburger or a pizza or a travel deal, but more to understand what is the likelihood that the features, the unknown features, are very difficult to extract features that a picture presents: color, texture, luminosity, different kinds of positions of the object, affected the propensity to travel. And then that we did offline. We scored each one of these images, now not calling it deal quality score, but image quality score. And that feature became a new feature in the online scoring, which is done online. So effectively, processing information about the deal, now about the image, and then incorporating it in the online scoring. Another challenge was this concept of propensity to travel. What does this mean? So when a user buys, especially local deals, they have to go to that place to redeem it, to that merchant, and certainly the willingness to go to a live event or a concert that, like I live in the South Bay in San Francisco, so the Bay Area. So my willingness to go and travel to San Francisco to go to an event is very high compared to the willingness I want to travel or how far I want to travel for a pizza deal or something else. So what we noticed is that radius or distance was not a good measure, not necessarily a good idea to incorporate it as purely a factor within the feature within the models. We had to consider directionality and what were the routes that people could take, almost like travel time, right? So that we know the convenience or the inconvenience that certain things have, and that is very different from category to category. So what we did there, we came up with this concept of geotemporal functional embeddings. Now, this is a constant you will see. I mean, yesterday they were talking about using embeddings to encode information that can be used later as features in your models. Now, the embedding concept is something that comes from, maybe a lot of people have heard from Word2Vec, but basically looking at sequences of, in this case, actions or purchases or redemptions in this case, but in the case of words, is the sequences of words that occur within a paragraph, and extracting some information that can really capture the underlying aspects that are not easy to expose as features. So one of the things we did was we looked at time as buckets of time and when did people actually redeem things, whether it was in the morning or in the afternoon, and what categories were these deals redeemed from. And then we also did a similar embedding on the IDs of the deals themselves. Not because the IDs were necessarily informative, but we did notice that people tend to go to places that are nearby, and there's a clustering of certain types of deals or location or merchants that are relevant to the user because of their location, because of their willingness to travel, again, depending on the time of the day and depending on the categories. So essentially, we're learning two embeddings. One embedding looking at, and these are the same events, so we're looking at redemption events aligned together. So one will keep the pair category time of day, whether it's morning, afternoon, or even whether it's weekend, morning, noon, or evening, and the other one would keep just the IDs. And with this information, and summing it up as one vector, we were able to capture redemption patterns that not only showed which kinds of categories were used the most or redeemed the most, but also gave us an idea that we can actually compute these embeddings and average them per user. So we would know, for example, once the embeddings, which are just numerical vectors, we would actually say, if I want to build a profile of this user, I could average the vectors across what he or she bought or redeemed, and that would represent more or less the type of deals that they're willing to buy at certain times of the day and in certain areas, because each one of these deals have location associated with it. So in that way, we basically brought down the location problem and combined it with geo and temporal aspect into an embedding space that we're able now to compute essentially user profile as well as deal profiles and be able to calculate the similarity. So once you're in that embedding space, you can compare and you can say, okay, now I know which deals the users tend to redeem. I can represent the user. I also have in the same embedding space the deals. I can compute the cosine similarity and have that as a feature in my ranking. Remember, this also captures the IDs of the deals that the users have redeemed. Therefore, it does capture location in the sense that each merchant, each deal is associated with a location in the map. Another use of embeddings, and again, this is use of deep learning, is this concept of query similarity. And as you might know, I mean, just here, words have multiple meanings. If I type in LA clipper versus nail clipper, obviously that's the word clipper is different. And the idea is, can I use a more sophisticated model to represent the association between queries and documents? So again, we used embeddings. So we basically looked at the words, in this case, Walt Disney word, and then we associated that with a query ID that would use to get to that deal that contained those words. So this is the same concept as doc2vec, but essentially you have a document, and then you are now trying to represent the whole document as a vector. So you use an embeddings of the words, and you associate it with an ID, in this case the ID of the query, and then use that as the ability, with that in mind, then you're able to basically associate similarities. And in this case, the query similarities that were shown yesterday, as well as when you talk about Word2Vec, so Apple associated with iPhone and Google with Pixel, and with those embeddings, we're able to add them to the models and use them appropriately. In other words, even if two words were not exactly the same, if they have semantic similarity based on the context they occur and the query that was used to get to those deals, they would appear here in this space that's very close by. In the context of browse, and this is the other third use case, the problem here was people, when they upload, merchants, when they upload deals, they automatically, or they self-categorize their deals in the taxonomy. So we have a taxonomy, and a lot of times merchants try to reach a large number of users by classifying to as many nodes as they can. So one problem we had is, how do we make automatic classification of deals into this taxonomical space so that when people browse, it actually reflects what they are? So what we did there is we used something called a taxonomy embedding. And again, these were, this is similar to the image recognition problem. We had samples, or in this case, a training set of properly classified title and descriptions and a label in the taxonomical space. What we needed to create is an embedding, again, a vector representation of the deal based on their title and description, and use that to basically classify that into the taxonomical space. So we use these red areas here, where like highlights the description and the title, and we created a classifier that was based on these embeddings. Again, why embeddings? Because now embeddings become an input to the model. So we're using this in combination with other features. And finally, the idea of similar deals. Now here we also created embeddings, but these embeddings were quite different. What we're looked at now is the sessions. So when users go and travel across the site, they're creating patterns of access. So every time they click on something and they browse and view something, ultimately some of those patterns of visit result in a purchase. Those patterns or sessions of users, looking them over many, many users, you can actually extract an embedding that will tell you which access pattern reached the same kind of deals. In other words, we can create a similarity in the space of embeddings of sessions to understand how deals are similar one to another. And this is not based on the content of the deal. We also have that information, obviously, based on text. But we wanted to understand what really led to deals and how you can compare them. So we created embeddings based on these sessions. Very similar to before. You're looking at the context there, and you're basically trying to predict a deal to vec. That is a vector that represents the deal based on the sessions that were used for visits. So in conclusion, we used machine learning to essentially solve 4 different use cases: the recommender system, home feed use case, the use case of browsing, so being able to look at the different categories and where deals actually fit within this category, the problem of search. When I type in a word, how do I associate that with my results? And finally, the similar deals. And by doing so, we created a series of embeddings. So it was not just one embedding. We call it doc to vec, deal to vec, and we also call it image to vec, that represented multiple aspects of the deals and the users, in the case of user sessions, and it created a embedding that can then be used in the online computation. So that essentially is moving away from traditional feature engineering to more using a combination of deep learning and machine learning to solve the problem. I don't think that machine learning or deep learning it will overcome machine learning or traditional statistical measurements and algorithms. I think the combination is a very, very powerful use case and statement. Thank you.